Hi and welcome, ladies and gentlemen. Today we're talking about Towers of Hanoi game, which is basically moving some disks around some pegs. Well, it is like this, that we have 3 pegs given and we have a certain amount of disks that can be arbitrary, but we have to have them sorted on the first peg initially. And then we want to move all the disks like that we have them sorted on the last peg. So there is the condition that we can only move smaller disks on top of greater disks. And that makes it a little bit more difficult to solve this puzzle, but as you will see, there's a straightforward algorithm to achieve that. Alright, so let's have a look at an example first. Here we have our 3 pegs, which are presented by these lines, and we have our 4 disks, everything sorted initially at our peg 1. So how do we get the next, or how do we get all the disks to our pegs? So what we want to do is we want to move at first the first peg to the peg 2 and the second peg to the peg 3. We basically want to empty one peg step by step and then free the next bigger peg and put it on the next bigger disks and want to add it on the next peg. So here we put the second disk to the peg 3 and then we put the disk from peg 2 to peg 3. Now as you can see, we emptied one peg again and now we have access to the third disk. So we move the third disk to peg 2 and then we can move the first disk of peg 3 to peg 1 and the disk of peg 3 to peg 2. As you can see there, the disks on peg 2 are now nice and sorted. So here to free the biggest or the tallest disk, we want to move the disk from peg 1 to peg 2 again. And then we want to move the largest disk to peg 3. Now that looks good already because that is where we want to go. We want to have the tallest disk on peg 3. So in the next step we move peg 2 to peg 3. So we free up, or we have our peg 1 empty now. So there we move the disk from peg 2 and then we move the disk from peg 3 to peg 1. What we achieved now is that we freed the next disk that we have to insert on peg 3. So we do that. And in the next step we just move the peg, the upper disk from peg 1 to peg 2 and then from peg 1, the disk from peg 1 that is the next that has to go to peg 3 to peg 3. So there's only one step left and that is to move the disk from peg 2 to peg 3 and so we are done. Alright, and the algorithm depends on the amount of disks we have. If they're even, as we had it right now, then we always do a legal move between A and B. And then we do a legal move between A and C, and then we do a legal move between B and C. And if the number of disks is odd, then we swap basically the first 2 moves. We just change the order. So we move from A to C and from A to B, and in the last step we do again a move from B to C. And there we have to pay a little bit of attention because we might have a success in between those moves already, so we can stop our program execution there. And what is also important, with move I mean a legal move. So a move from A to B might be a move, as I said, from peg A to peg B, or from peg B to peg A, if that is a legal one in this case. So let's implement that in Python. For that I create a new file here and I call that Towers of Hanoi.python. And let's implement at first our pegs. For that I need a number of disks, I call that num disks, and initially we have our 4 here as in our example. And then we have our 3 pegs. So we have here peg A, and let me initialize that as an empty list for now, peg B, and peg C. So what we can do now is we can initialize our peg A already that we have the disks sorted on it. So I will simply use numbers, and I say if the tallest disk, in this case the disk 4, has the number 4, and so on. So what we do here is we create a for loop to fill in our peg A. So here I say that is our disk, for disk in range, and there I want to start with the tallest one. So here I say num disks minus 1, that is where we start, and I use there the disk 3 is the tallest one and disk 0 is the smallest one. So we have it indexed by 0. So here I also want to go to 0. Since the outer border is not included, we have to use -1. And then I define the step size of -1. So, and that gives us already a sorted peg A. If we print here peg A just for seeing that it works, so we can print here peg A. Let's run it quickly. And there, as you can see, they're sorted in the right direction. On index 0, which is the lowest in the list, we have our 3, that is the tallest, then 2, 1 and 0. Alright, so let's go ahead with the algorithm now. So we call now the function, or we don't actually need to make a function. I want to say here while not success, or let's actually say while true, that is also fine. Then we say if our amount of disks is odd, so if num disks modulo 2 is equal to 0, then our disks are even number of disks here. Then we want to go in and say here move A, B, move B, C, and we want to go in and say move, here we have to use AC, and then we do here a move B and C. So we need the move function actually. So for now I create a function here, def move, and there I say peg 1, peg 2, just to not get confused with the global naming of peg A, B and C. And I say here that performs a legal move between peg 1 and peg 2. Alright, so for now I just say pass here. We will implement that in a minute. And here we have to use actually peg A and peg B, peg A, peg C, and here we have to use peg B and peg C. Alright. And now I want to copy these 3 lines here, and I go in and say else. So the number of disks is not even now. So what we need to do is we have to swap our first move. So we basically move at first from peg A to peg C and then from peg A to peg B. And with that, we are almost done. What we have to do in between here is we have to check if it is successful. So we can say it is successful if all the disks are sorted on the peg, on peg C. So if the number of disks is on peg C, because we will use the condition just smaller on top of the other. So we can say here if success, or let's call it if is success peg C, then we want to return. And we do that after each of our step here. And we will do that after each of our step here. I didn't do it after the peg C here, because actually we can remove that here and take that out of our if-else cases, because we do it anyway afterwards. So I go in here and say it like this, and we don't use return here, we use a break. And then I want to go in here and bring that in the right format. Alright, and that looks good. We just need to implement our is success. So def is success, and there we have our peg. And for that I say checks if the amount of disks is on peg. And there I say if peg, or if the length of our peg, so basically the amount of disks on our peg is -1, or no, is equal to our, and we called it up here num disks. So num disks, we use there the scoping of Python. Then I say return true, otherwise we return false. Alright, so good so far. Let's implement the move method now. So there we have to take a little bit care, because we have to check if it is a legal move. Do we move from peg A to peg B, or from peg 1 to peg 2, or do we move from peg 2 to peg 1? So we have to check at first if the length of our peg 1 is smaller than 1. Then we want to append the disk of peg 2 to peg 1. So I go in and say peg 1 dot append, and there I say peg 2 dot pop. What the pop method is doing, it removes the last element in the list and returns it. So we get here the last element in the list and append it to our peg 1. And automatically we remove it from our peg 2. So this we have to extend a little bit here. We have to do it a little bit more precise, because what can also happen? We also have to check here and the length of our peg 2 is actually greater than 0, because otherwise we can't take an element from peg 2, or we can say here, we have to use here another and now we have to check, is the amount of disks of peg 2, or is the last disk of peg 2 actually a taller disk than the disk on peg 1. So we say here and peg, here peg 2 with -1, I can access the last element in this list, is greater than peg 1 -1. So that means we can actually move the disk from peg 2 to peg 1. And in all other cases, we say peg 2 dot append peg 1 dot pop. So we take the element from peg 1 and put it on peg 2. Alright, so let's have a look if that works. We can go in here now and say print peg A, print peg B, and print peg C. And that doesn't work yet completely. Alright, and here is a little mistake in it. Alright, at first we have to check here, is peg 2, is the length of peg 2 greater than 0? And is the length of peg 1, is this smaller than 1? Or is the length or is the item on peg 2 smaller than the item of peg 1? And then if we run that here, we actually achieve the right result. Let's check it also with an uneven number. Let's say 5 here. So if we check that now, as you can see, that works completely fine. Alright, ladies and gentlemen, that's it for this video. As usual, you'll find the source code down in the description below. I really appreciate every like or subscriber to the channel. And yeah, tell me down in the comments below what you think about this video. Thanks for watching, have a great day, bye.